Good afternoon, everyone. My name is Maria Schatz, and I am a scientific program manager for the NIHS Office of Data Science. It is my pleasure to welcome you to the ELK seminar series. By the way of background, ELK stands for Environmental Health Language Collaborative, and our mission is to advance integrative environmental health research by promoting access, use, and harmonization of data through interoperable terminologies and best practices. Our goal is to become an active community of practice that acts towards identifying use cases and needs, prioritizing activity, and exchanging information, ideas, and expertise. You can become involved with ELK by visiting ELK website, joining our listserv, or contacting directly ICF support team, Charles Smith, or myself using the provided emails. So today's seminar is a part of a new series. It starts the 2026 fiscal year ELK webinar series just 3 months later than we intended, and it's a part of a series of talks describing work progress in NIHS funded data, the environmental health data standards program. And I will let Chris Duncan, who is a project officer on this program, to present our speakers and maybe tell a little bit more about the program. Chris, please take it away.
Thanks, Maria, and thanks everyone online for joining today. As Maria mentioned, my name is Chris Duncan. I'm a program administrator in the extramural division at NIHS, and it is my pleasure to introduce our speakers for today, Dr. Mollie Cummins and Dr. Ram Gouripeddi, to kick off the series of ELK webinars focused on highlighting ongoing data and metadata standards efforts in the environmental health sciences. Dr. Mollie Cummins is a professor of nursing and an adjunct professor of biomedical informatics at the University of Utah, and she is a John M. Huntsman Presidential Chair. She holds a PhD in nursing science and information science from Indiana University, and her work has addressed diverse challenges in biomedical informatics and exposure health informatics research, ranging from interoperability of poison control exposure data to informatics infrastructure for sensor data and metadata. At the University of Utah, she serves on the leadership team of the Center of Excellence for Exposure Health Informatics. Dr. Ram Gouripeddi is an assistant professor of biomedical informatics at the University of Utah. He earned his Master of Science from Arizona State University and his medical degree from MGR Medical University in India. He specializes in developing informatics methods for exposure health and translational research. And he is an assistant director of informatics for the Utah Clinical and Translational Science Institutes, as well as the associate director for research for the Center of Excellence for Exposure Health Informatics. Today, Dr. Cummins and Gouripeddi will be speaking about a project that they co-lead on sensor and metadata for analytics and research and exposure health, also known as the SMARTER project. And this project, as Maria mentioned, is supported through NIHS's initiative for accelerating data and metadata standards in the environmental health sciences. So with that in mind, let's move on to the presentation. Welcome, Mollie and Ram. Pass the floor over to you.
Wonderful. Thank you so much for the kind introduction. Formally, we call our project Community-Driven Sensor Metadata Ecosystem for Exposure Health. That's the title of the grant that's funded through NIEHS. We have no relevant relationships with commercial interests to disclose. And we'd like to acknowledge funding sources for this work, which include NIEHS, NCATS, and IBIB, and CHP resources that are partially funded through an NIH Research Instrumentation Award. The content is solely our responsibility. The title slide I just showed you, the formal title of our grant is quite a mouthful. We call the project and what we're building through the project SMARTER, which stands for Sensors and Metadata for Analysis and Research in Exposure Health. SMARTER is funded by the NIEHS under their Data and Metadata Standards program. So this project is part of NIEHS's broader initiative to advance environmental health data and metadata standards. Data standards are a strategic priority for NIEHS because they enhance scientific rigor and reproducibility in exposure health and exposomics, environmental research. Importantly, these standards support FAIR principles. We want to make data findable, accessible, interoperable, and reusable. And ultimately, this improves the validity and comparability of health studies and lowers barriers to data sharing and interoperability. We're one of 5 awardees in this program, all focused on advancing community-driven data and metadata standards with a particular emphasis on collaboration, communication, and open sharing. So we particularly appreciate the invitation to speak today. The awardees in this program, we share information with each other. We connect on points of synergy and collaboration. Last year, we met in person at NIEHS. On Monday, we're having a virtual meetup to share progress and work collaboratively. A bit of background. We know that environmental exposures have a profound impact on human health, but fully integrating these influences requires integrating vast amounts of real-world data from a variety of sources and at varied temporal spatial scales. While these data are valuable, the major challenge lies in how we manage the data, use the data. Currently, there's a gap in informatics tools that enable researchers to efficiently share, locate, assess, reuse environmental data. This gap stems in part from the absence of standard comprehensive metadata that enables data integration. This is the critical descriptive information, the data about the data about how the data were gathered, processed, and structured. Without proper metadata, reusing data is problematic. It hinders reproducibility and slows scientific progress. So existing metadata approaches in exposure health, as this group probably well knows, are largely inconsistent and ad hoc, and that limits the ability to repurpose or integrate data sets from different studies. The circumstance creates fragmentation within the research community, and investigators often lack incentives or resources that help them create or curate metadata for data reuse. Tools that would facilitate discovery, harmonization, storage, and publication of metadata are scarce and face barriers to adoption. Our long-term goal is to overcome some of these obstacles by optimizing informatics systems and processes that support exposure health research, exposomic research, enabling more precise insights into how exposures affect health. Building on our previous work, developing an exposure health informatics ecosystem, we aim to advance these capabilities further, particularly in sensor-based exposure health research. We're pursuing 4 aims designed to enhance metadata tools. First, we developed logical models to harmonize sensor metadata through a community-driven approach. This involves collaborating with sensor developers and researchers to identify relevant metadata elements, create a standardized logical model that reflects the community's needs. Public feedback is solicited to refine this model, ensuring broad acceptance and utility. The expected outcome is a shared standardized logical model for storing metadata, and one that is available in common data exchange formats like XML and JSON. Second, we're creating a user-facing metadata repository designed with user-centric principles. This repository will enable researchers to easily find, submit, browse metadata related to sensors and instruments, fostering data harmonization and reuse. And the repository will function as a centralized library supporting metadata-driven data sharing. Third, using the logical model and the structured metadata will enable the transformation of exposure health data into event-based formats that include spatial and temporal information. Developing specifications and logical models for this standard format allows for enhanced data reuse and the creation of longitudinal exposure records that can be analyzed consistently across studies. Finally, we'll develop prototype workflows that demonstrate how this can be practically applied to create semantically consistent, AI-ready, and fair exposure health data. The workflows modeled using UML diagrams and supplemented with documentation, sample data sets, will guide researchers in integrating diverse data sources effectively. And together, we think these efforts will result in a community-driven, reproducible, scalable metadata and data management tools. Ultimately, this can help us leverage real-world data to advance our understanding of environmental impacts on human health. SMARTER builds on our prior work at University of Utah, where we created the Exposure Health Informatics Ecosystem, EHI. EHI is a comprehensive standards-based open source informatics platform that enables semantically consistent, metadata-driven, event-based management of exposomic data. Its primary goal is to address key challenges in exposure health research. It is really an ecosystem, a collection of hardware and software that supports acquisition and integration of heterogeneous data. It can be used to generate high-resolution spatiotemporal grids of exposures. It can be used to fill data gaps using computational modeling and to characterize uncertainties associated with the data. It supports diverse translational research archetypes. This diagram shows basic groupings of EHI software and hardware artifacts, which include participant-facing tools, a data acquisition pipeline, tools for computational modeling and uncertainty characterization, and more. SMARTER adds the components that you see outlined in red and marked with the SMARTER logo, the small gray brain logo. These include the graph metadata repository, its user interface, the sensor library, as well as some advanced analytics. A core motivation for SMARTER is to make sensor metadata fair. We want metadata to be findable, helping researchers discover, organize, and standardize sensor metadata. We want it to make it accessible by storing metadata models in a shareable repository. Interoperable, sensor data can be assimilated into common formats supporting spatial and temporal analysis. And reusable, enhancing sensor data with metadata to enable AI and advanced analytics. Additionally, a major focus of SMARTER is engaging the research community. We formed a national expert panel of exposure health researchers that meets regularly to provide input and feedback. We also invite public comments via platforms, including GitHub and REDCap surveys. User-centered design is fundamental to our approach. We involve users throughout requirements gathering, prototyping, usability testing to ensure the metadata repository meets real-world needs. Here's a snapshot of our national panel of exposure health researchers. This panel meets quarterly, also on an ad hoc basis or in subgroups as needed for different aspects of what we're doing. It includes both local and national experts, and it includes representation of the military, the private sector, and the EPA. We post opportunities for public comment on our website. Here's an example. We publicize them through our mailing list and LinkedIn. We publish the artifacts on GitHub and collect input through REDCap surveys. And through user-centered design processes, we're working to ensure that the metadata repository, the user-facing component of it, is built based on a deep understanding of how sensor metadata is used by diverse stakeholders. It includes scientists, researchers, but also members of their team, data managers, statisticians. It also involves sensor developers across all study phases, ranging from deployment to analysis. I'll share more detail on how we're doing that in a moment. Currently, our communications are anchored by a website, which serves as a central hub for information about the project. We put out a quarterly newsletter with updates and information, and we share that in a basic fashion on LinkedIn and partner with like-minded projects like Nexus, for example, for redistribution. This is our project website. Please visit and sign up for our mailing list. We'll provide you with the URL at the end. This is also a way to contact any member of our team. It's also easy to Google. Just Google the Smarter Project or Smarter Exposure Health. Now let's take a closer look at user-centered design on this project. So coming into the project, we had some foundational knowledge of the way metadata is used in environmental health research. This was based on our experience as a PRISM's Informatics Center. We had a good basic sense of who interacts with sensor metadata, and we'd already defined some preliminary use cases and requirements as they intersected with the function of EHI and our work on PRISMs. But to effectively design a metadata repository that people will use, we needed to dig deeper. This slide shows the timeline of our work in defining user requirements thus far, beginning with our foundational knowledge, progressing to prospective research and analysis with our target users, and identification of a list of candidate requirements. And as you might imagine, this wasn't if the candidate requirement list was in effect a wish list for Santa. And not all the requirements were actually feasible or within the scope of Smarter, unfortunately. At that stage, we used the expert panel. They reviewed and prioritized the requirements for us. And then we conducted a technical review with our internal leadership and software development personnel to analyze that list in terms of scope, budget, and technical feasibility. And through that process, we were able to finalize a list of requirements. Then we developed a formal requirements document to guide subsequent design. One of the ways we built understanding of user needs was through semi-structured interviews with target users in varied roles. It was essentially qualitative research aimed at understanding the needs, preferences, and pain points of environmental health researchers regarding the selection, deployment, and integration of sensors for their research studies to inform requirements. We then conducted deductive content analysis of the interview transcripts guided by the HITREF framework. We had a number of findings from this work. A manuscript describing those findings is currently under review. In essence, researchers consider multiple characteristics of sensors at varied stages of a research study. This can range from initial sensor selection during study design to monitoring a sensor deployment during the study, during data collection, to processing and analyzing the data that results. And in telling us about their experiences, their needs, their challenges, the participants expressed a clear need for support, standardized metadata, and flexibility in how they're able to use the data that results. Here are a couple of snipped images from our user requirements document, an excerpt from the table of contents, and an example requirement. Each requirement is structured in this way. We define it, we connect it to a real-world user experience, and we detail a DOD, a definition of done. And that allows us to focus our development efforts and evaluate our progress. We also developed a series of use cases to guide design and testing. Here is an example of one of our user flows. This depicts a principal investigator during the planning stage of a fictional study, and it delineates their decision points and information needs. This allows us to design effective testing scenarios. With the user requirements document in place and having defined those use cases and user flows, we were able to proceed to design. This is one of our wireframes from earlier this fall. A wireframe is a visual blueprint for the software interface. We create them using Figma, and we can make these wireframes behave similarly to actual software by hyperlinking visual elements on different screens. This allows us to engage in iterative user-centered design cycles where we test aspects of the design with our target users, make changes, then retest. We completed multiple cycles this fall, and currently we're moving to higher fidelity prototypes with more sophisticated hyperlinking. Eventually, these prototypes will be handed off to the software developers to actually build. We anticipate progressing to the build of the design, the actual user interface software development in early 2026. 2026 is going to be a big software development year for our team as we work to move from high fidelity prototypes to functional software with high usability for our target users. If you're interested in helping us out by participating in some brief online testing sessions, we are always looking to test with different researchers in different roles with different perspectives. Please do send Ram or me a note or reach out via the website and we'll follow up with you. And with that, I'll hand off this presentation to my colleague, Dr. Ram Gouripeddi. Thank you.
Thanks, Dr. Cummins. I will share my screen. Okay, I will continue give an update on our work and what we are thinking about the implementation of our findings from the user requirements analysis as a part of this project. So to summarize the key requirements that we identified as a part of this work, I put the entirety of the user requirements document into 5 categories. One is that the sensor technology, the metadata store needs to be agnostic to the sensor technology. The store itself needs to be abstracted so that it can be versioned as and when there are changes to different metadata attributes of importance as we receive more feedback. The need to support heterogeneous sensor technologies, the metadata of heterogeneous sensor technologies, support the entirety of the life cycle of how a sensor might be used in exposure health and exposure health research, and support multiple metadata needs, including discovery, that is researchers having the ability to browse available sensor technologies for use in their studies, ability to publish sensors that have been selected, maybe along with publications, and data integration. And with this context, I will give a quick overview of what we are doing on each of these functional requirements. Okay, so first we refine the sensor specification itself from the additional feedback we received through Smarter. And one of the key components that we were able to we addressed is the need for heterogeneity And we took this core, a combined definition of what we can call as a sensor, and divided it up into 4 components. We call a composite of one or more sensors as an instrument, a sensor as something that can measure one property, physical, chemical, or biological, and each of those properties are measured by one specific method. And more broadly, sensors can range from nanosensors to satellites and can be mobile, in-home, or general ambient sensoring like EPA monitors. And in a sense, they might be equate to the general, specific, and personal domains of the exposome. And to understand the entirety of exposure health, we also expanded to include sensors that are physiological sensors that measure responses to the environment in addition to measuring the environment as well. Our next step was in trying to abstract the sensor model, the meta model structure in which we are using to generate we are implementing the logical model using previous work we did through a project called Open Further. Here we combine different artifacts of different metadata specifications, including OMG, Dublin Core, and ISO standards, where we represent everything as an asset. There are properties for every asset. There are associations between assets. The associations also have properties and resources, and everything about something specific, a particular domain can be organized into a namespace. So what this allows us to do is to expose the metadata in any of these higher level specifications and implement the metadata in different database technologies. But as you can see here, given the asset and association type of relations, we navigated to using a graph-based technology, but it can be implemented in any other database technology. Our next finding was the need to support the entirety of the life cycle of how a sensor is used within a given study. So this relates to the researcher, knowing what the sensor capabilities or characteristics are, which are represented in the instrument domain, how a sensor is deployed within a study or a data collection. So characteristics of whether it is in-home, which part of the home or outdoor, when was it calibrated, and so on and so forth. And the last domain that is actually about the measurement itself, the data coming out of the sensor, which is represented by the output domain. And we organize each of those domains into entities and attributes. And here are the core entities. So the instrument, as I said, is a composite of sensors. So within the instrument, you have detailed information about each sensor, the organization the organization that the instrument was developed or is held with, any documentation that is unstructured is a part of the document, is stored as the document entity, information about the validation of how well the sensor actually measures with a gold standard, information about measurement, so what particular property is being measured, what are the characteristics of when that measurement is valid. For example, if the humidity went over a certain threshold, then is the PM2.5 level valid or not? Some sensors collect samples, which are then analyzed at a later time using different technologies, including mass spec. In that case, the sample collection entity describes the characteristics of how the sample are collected and then to be analyzed. The instrument data transport entity deals with the information communication layer of how the sensor sends signals out using different communication protocols, Wi-Fi, Bluetooth, so on, and what might be the end target database data store to which the sensor technology needs to point to. The deployment domain talks about characteristics of how a sensor is deployed within a study. What is the environment? When was the calibration done? Is there any configuration done to the core sensor technology to make it amenable to the design of a particular study? And finally, the output domain, which talks about the property that is being measured, units of measure, so on, and similar characteristics of a collected sample if it's collecting a sample. The sensor is collecting a sample. We then validated this with different existing sensor technologies, and some of them also provided by the expert panel to make sure we're capturing sufficient metadata and all the attributes relevant to different sensors are within the scope of the sensor specification. As I said, because given the very relational nature of how sensors and their metadata attributes relate to each other, we implemented this as a graph, which allows us to extend and modify in a very rapid fashion. Here is an example of an air use sensor developed by at the University of Utah. This is just an exemplar, but you can see what the graph technology can similarly store metadata of any other sensor technology. The color here represents the different entities corresponding to the specification I showed in a previous slide. This way, we would with the attributes and properties for across the different sensor technologies or instruments, an end user would be able to address different types of questions. For example, give me all the sensors that measure a PM2.5, or give me all sensors that measure PM2.5 and can be deployed indoors, or give me all PM2.5 sensors that require only a battery source and do not or require battery and use a Wi-Fi protocol for communication and so on, and very much in a sense in a library of books fashion. And to address the other functional requirements, what we are doing currently is expanding the metadata repository to serve three primary purposes. One is as a library, so for the use of a researcher, human consumption of the information, for allowing for browsing, selection, and submission of sensor metadata, ability to import and export exchangeable formats like JSON or XML, and also to use it in data integration pipelines. So Dr. Cummins showed some examples of the wireframes that we are developing for the sensor library. So in the next few slides, I'm briefly going to touch on the data data pipelines aspect of how the metadata repository is being used. And again, we'll go over this as with EI as an exemplar, but the endpoints of the metadata repositories, which are APIs, can be connected with any data platform. And I will briefly talk about how how Smarter is currently in action within this platform, but eventually once we have it working with EI, we will share it as a product that can be connected with any other data pipeline. So core facets here are the library, which talks to the repository, and the end user researcher can browse, find a sensor technology of relevance to them and use it for their particular study. The graph metadata repository also connects to data acquisition pipeline to enable study processes and sensor deployments, and finally for data integration through event document store and advanced analytics. So what the Smarter Sensor MDR allows us, or us being any data team, to do is to make a data pipeline agnostic, to any measured properties, to any sensor technology, any particular study design, and also any specific IT infrastructure detail. And enables this metadata-centric approach enables data pipeline resiliency and automation of methods in enrolling IoT and other sensor devices. So what this ends up being is, for future studies, as a research team would need to either have their sensor metadata already, the sensor metadata needs to be basically discovered and authored into the MDR, and then it can be consumed through the pipeline for study data process, for enabling study data operations, deployments, and data integration. If it's a new sensor, then the metadata of that sensor needs to be discovered and authored, and then it's available through the MDR for rest of the processes. As an exemplar, one of the things that this enables is sensor deployment management. Every sensor has different characteristics. Once we have the metadata in the MDR, and here is an example again for Airview, deployed within the homes and work locations of the study team, we can easily modify programmatically dashboards that can monitor and observe the health of the sensors during the study operational phase without having to develop custom dashboards for every sensor that needs to be deployed in a prospective study. And it also is helping us in doing data integration using what we call an event-based format. And I will go over this very quickly in the next few slides. So one of the big challenge in exposure health is that we are talking of very diverse root objects. We are, of course, talking about a person and a person's health, mostly clinical data, either coming out of medical records or a part of the study collection itself, and sensors that can be assigned to an individual at some times, at an extreme if it's a personal sensor, or it is assigned to a location, maybe a residence. Then you can debate whether it is a person's exposure or at the other end is ambient sensing, where you might have one or a few monitors in a large geographic region. So the challenge in integration is how do we consistently integrate this multi-scale, multi-model data with different temporal resolutions and representing different root objects, person, environment, and so on, into one consistent format, which and then can be used for that is primitive enough to support different analytical approaches. So for this, we define what we call an event. An event is basically an observed physical reality. It can be a PM2.5 level. It can be a clinical condition, all of which have spatial and temporal coordinates to say where and when something happens, so that you can accommodate spatial and temporal reasoning to within the data and use this primitive structure to create more advanced analytical models as needed for a particular study design. We came up with 6 primitive types or event types: sensors, clinical, participant-reported, biospecimen-derived computational models, and other aggregate forms like census. But here I will primarily talk about sensors. So what we do is use the metadata from the metadata graph metadata store and transform the raw sensor reads into an event. Here is an example, a simple example of an event for temperature recording, which has an observed entity, which is air temperature, a location, and a timestamp. Similarly, events for a clinical condition of when the condition occurred. So maybe it's an ICD code or a SNOMED code, and a timestamp and a location of when this were recorded or occurred. Now this format allows us to easily transform using a data lake approach, capture the data in primitive form and easily transform into specific analytical models, for example, say OMOP, and then allow for spatial and temporal reasoning. So this is again a work in progress and where we are at this point of time. And I will stop there. Okay, but just before I stop, I would like to acknowledge our team, some of whom are on the call, and also all our partners, experts, and collaborators, also some of whom are on the call, for all your help with this project. And we'll stop there and we can open for any questions.
Thank you so much, Aram and Mollie, for your great presentation. So we've got some time left for questions. So I think Chris Schnur is going to allow you to unmute and raise your hand as well, or you can add your questions in the question box. All right, so we've got one from Brian. Okay, can you share more about the process you use for creating the data model? He's also curious about how the technology pieces are integrated and what you're using for the graph database.
Okay, sure. So the process that we use for data modeling is an iterative approach. We started with doing a literature review to find what attributes are of significant to exposure health that describe sensors. We then we came up with an initial conceptual model. We took it to the expert panel and had them critique it, and then came up with the next version. I also asked the expert panels to give us example sensor technologies that we can use to validate the logical model, and then came up with the next set of next version of the logical model, which we now host on GitHub. A link I shared on the slides. You can also find it on the Smarter Exposure Health page. And we, as Dr. Cummins mentioned, we continue to look for feedback from the community on the attributes, and also to supply us with any sensors that might be of relevance to the community. To the second part of the question, we are currently using Neo4j, but that is not to say that any other graph, or for that matter, any other database technology can be used to take the specifications and create a separate store. We eventually hope that this store would be available with NIHS and to the larger exposure health community to submit and interrogate for sensor metadata. Don't know if I forgot any other part of the question.
Yeah, I think you pretty much covered the question there. Brian, if we miss something, just let us know. Okay, Vasu, I think you're up next.
Hi, thank you for that presentation. One question I had is, sometimes when you come across particular data elements, they can go in one of two places, and it's sometimes difficult to choose. I'm thinking in particular of the calibration that you showed earlier in the that element. Now, calibration could be part of the instrument or sensor. Maybe it was done at the manufacturer, or it could be part of an effort to essentially recalibrate, maybe with co-location during a deployment. I see you have it in the deployment. I know this is getting into the weeds a little bit, but I'm wondering how you made those kinds of choices, and sometimes they're difficult ones, I understand, but it could kind of go someplace. Some of these could go in either place. So that was my kind of comment and question.
Yeah, Vasu, that's a great question. And so the way we organized it into 3 domains was from 3 perspectives. We can think of the information domain as a knowledge store. So how can you calibrate this sensor is the question that the knowledge store, the information, the instrument domain will address. This next question of how a particular sensor was calibrated, when it was calibrated as a part of a study, is the operational metadata that goes into the deployment domain. So what is done as a part of the study is the deployment domain. What is more informative to the end user is the instrument domain. Now, sometimes I completely agree with you. It may not be very clear if you're not doing the calibration as a part of the study, but we have left placeholders for both locations with relational linkages between the information or knowledge component to the operational component. So end user can navigate across the 2. I think I would take the example of an EPA monitor. We may not always know when was the last calibration done, because it's not in the control of the study team. But we can always share what is the life cycle of calibrations and what is the method of life cycle calibration within the instrument domain. But
thank you.
Yeah, but I'm sure we appreciate more feedback as we and collect more individual level metadata of sensors. I'm sure we will appreciate your feedback as we move forward.
Thank you for that. Good question there. Okay, Elaine, you're up next. See, Elaine, can you unmute?
She should be able to.
Okay. All right. Elaine, we're not forgetting about you, but maybe we'll go to Maria and then come back to Elaine. Maria, go ahead.
So I have a kind of general question. I understand that you're about the repository. So I understand you are trying to present metadata about different sensors in a standardized manner. And suppose you have a list of, you have a data model, all the elements. So two questions. One is, how do you decide what sensors to describe? Or are you trying to describe the entire universe of the sensors? And second is about not model, but the language standards. How do you decide what to call the elements? And how do you ensure that, you know, you use the same terms, you use the same terms across the sensors if you can, because they might be originally not called the same. But how do you harmonize this?
Dr. Cummins, you want to take it? I know that you have to drop in a couple of minutes, and then I can address anything else.
Sure, that sounds great. We're really building a system, but not operating a library at this point. So I think part of your question is sort of governance and scope for operations. And we're not quite at the operations phase yet, but we're trying to build a platform that can work. It can really facilitate a number of models. In terms of populating the library and adjudicating different versions of metadata, we're doing some exploratory work right now. We do have a one manuscript under review and a couple presentations we've given about an LLM-based approach we have for extracting metadata from documents. One of the barriers to managing metadata is researchers just will not take the time to document an extensive list of metadata about a sensor. It's just, it's like pulling teeth to have people fill out forms that could take them quite a bit of time. So we need to find creative ways to populate populate the metadata and adjudicate different versions of the metadata. So we're in the exploratory stages for some of that work. And then Ram, there's some other points to her question that maybe you can address.
Sure. So I think the semantics are the vocabularies for the values for each of the attributes was the second part of your question. One, I think there are different standards used across this space, from sensor engineering to what operational people do for deployments, to what clinical folk understand about sensors. So we, very early on, we knew that just directly approaching the, to come up with one ring that rules them all is not going to work. And that's why this metadata approach. We understand that depending on the end user, there might be a need to, if it's a person probably who's developing a sensor technology, they probably would want to use vocabularies that are more in their space. So we are, for each entity and attribute, we are coming up with a specification of choice of vocabularies where possible. Sometimes it is not possible. Some of them are very free text entries, and we don't control some very descriptive things like deployments where it's indoor, outdoor. There are also some cases where there were studies where investigators wanted to know information that it was under a vent in the house. It's more manageable to standardize the output or the measurement part of the data itself, which will be accomplished by the data pipeline, the federation platform in generating the events. to a set of standards as agreeable by the experts for demonstration, but with the flexibility to provide data in any other standard of choice.
Thank you.
Thank you. All right, Elaine,
Yes,
we're back to you now.
Mute button. Sorry about that. This has been an excellent presentation. So thank you so much. Really, really appreciate it. It just takes me a little while to assimilate it. I was very encouraged when you talked about citizen input on that, especially on something that's quite complex. And so if one took an example of what's called an event from a sensor standpoint, have you gotten the level of detail of input from citizens, what an event means for them? Like, for example, if you're looking at air pollution, the idea it might be one of the many different ways that we think about respiratory impact. So the question is about linking the phenotype that's either clinical or observed by the citizen and being able to get them to come in and give productive comments on what you're calling as events, because these are the complexity of this is fairly dramatic. So how have you achieved that or working on it?
So we are working on it. That's our next aim goal, which we will be actively working from middle of next year. Right now we can generate events. I think you bring up a very, I will be open to receiving your feedback after the call on what we are doing. We are trying to keep the each event to its most native or primitive form. So something as an event that you are describing from a phenotypic perspective, which can be derived. So like if I would take a clinical event, for example, if at the most primitive form, if a patient is coming to the EHR for care and we record in the EHR a diagnosis of asthma or an infection or whatever, multiple times, each of those at the primitive form can be a clinical event, or each of those measurements of PM2.5 can be an event. Now, these events can be assimilated to higher level events to say this is the duration over which the patient has asthma, or this is the duration over which the PM2.5 was spiking, or this is what we are doing right now is also identifying temporal sequences of significance using a method called shapelets. So to say that this is an event that is described by this shapelet that might be more important to a change in a clinical phenotype. But at a data lake level, keep it as its most native and primitive form. And so every individual study or investigator might be able to take the native form and generate higher level forms required for their study analysis.
Thank you. Thank you.
Great question. And if you can hang on for a couple more minutes, Ram, there's one more question in the Q&A box from Charles. Charles was glad to see the reference to OMOP. Have you looked at the proposed OMOP GIS extension from the OMOP GIS working group? And does that work fit with the data metadata you have, or are there challenges with it?
I think it fits very well. I've seen the standard. I'm part of the group, but not able to attend right now. But Charles, I think we will be talking to you soon, maybe in the next part of the of 2026, to get some feedback on the events and how it connects with the GIS OMOP working group and other efforts as well.
Great, thank you, Ram. So it looks like we're out of time, but in closing, just want to thank you, Ram, and thank Mollie for your excellent presentation today and your thoughtful insights on all the Q&A. And I'd like to offer a special thanks to Maria Schatz and the NIHS Office of Data Science for organizing this webinar and for the opportunity to highlight this really important topic. Before we sign off, I'd like to share one quick announcement. The next ELK webinar will be on Friday, January 23rd from 2 to 3 p.m. Eastern Time. And the speaker will be Dr. Sabrina Toro, and she'll be discussing standards for annotating zebrafish toxicological exposures and their phenotypic outcomes. So with that, I'd like to say thank you again, Mollie and Ram, Maria, and everyone in the audience today, and hope you all have a nice weekend.
Thank you so much, Chris. Thank you for moderating. Thank you, Ram and Mollie. We will see you on the next webinar.